Okay, so this lecture is all about trees and it's all about decision trees. So we've already done quite a few techniques for kind of class prediction. We did k nearest neighbors, we did discriminant analysis, we've done logistic regression. So this is the final technique that we can use for class prediction. Now there are a lot more techniques available, but for this class, this is kind of about as far as we're going to go. So let's just kind of have an example. We're trying to predict if people are asymptomatic and I can't spell asymptomatic for the coronavirus. And imagine we've done, we've tested if people have the antibodies, and then we also test them on whether they experienced any symptoms. So we have a sample of people, and we have some kind of, health information. And all of these people have had the coronavirus through kind of antibody testing, but we'll have one if asymptomatic or no symptoms, and 0 if we have symptoms. It seems like the wrong way round, but we're testing for asymptomatic. So the first thing we do is we have all this information. So we have things like age, body mass index. We have various like health indicators, exercise and stuff like that. So what we're going to do is we're going to think, what's the most important thing? Well, a lot of young people are asymptomatic. So let's just say we're going to split. And here we're going to have age greater than 40. This is basically my sample. So at the top, it's like everybody in the sample. And here we have, we've got the ages greater than 40. And we have yes. And here we have no. So here, like only... maybe out of 100, let's just say we have 100 people in each of these branches. We have 200 overall. We'll say we have 25 who had no symptoms. And we have 75 who have the symptoms. Okay, so this is a majority class, and so we choose this here. And here, this is a majority class, so we choose this here. So this is my training data set. Now what happens is when we have my test items or new items, we automatically say if you have ages greater than 40, we kind of classify you as having symptoms. We guess that you have symptoms. And if your age is less than or equal to 40, we classify that you don't have symptoms. So it's a very simple classifier based on kind of one particular kind of feature. Now, how do we evaluate how good our training error is? So let's go back to my black pen. Let's do a blue pen. My training error . Now this is going to be 1 minus max K P M K. Now what does this mean? Well, this is the probability of, these are the two different classes. So we have the no symptoms and the symptoms. And basically we're looking for the maximum fitted probability. Now, so here the probability is 0.75. and here's the probability is 0.25. So in this guy, we have 0.7, and here we have 0.3. So we're going to say that, all the ones coming down this branch, my error is going to be 1 minus 0.75 is the maximum, equals 0.25. And here, if we look on this side, my error is 1 minus 0.7, which is the maximum, equals 0.3. And we can actually kind of weight this. So say we have 100 items coming down here and 100 items coming down here. It'd be something like 100 times 0.25 plus 100 times 0.3 all over 200. So we'd have the, average error. Now, this isn't particularly very good. So what we would do is we would kind of go on a little bit. Let's move it up a little bit. And then we'd say, okay, we can do this a little bit further. So if all these people are over 40, we'll say, people who have a BMI greater than, say, 25, and that'll be a yes, and that'll be a no. And then we could say something like, if these people with BMI, do you exercise? We'd have yes and no. And then we'd kind of carry on getting my model more and more accurate. Now, there's a few things here. We can have like discrete predictors, which we just take as is, or we can have continuous predictors where obviously we have to decide on some cut point. And the algorithm decides on an appropriate cut point. Now we could carry on until each of my training data sets was in its own little bin. So we could have, if we have like 100 items, each would be in its own little what we call leaf node. However, this is really going to overfit the data based on the training data. So again, this is a little bit like regression. As you build more branches into your tree, you get more accurate, but eventually you're going to get to this stage of overfitting, which is where cross-validation comes in. Okay, so I actually put together a few slides for this on tree prediction. So this is an example. This is an example from the textbook of a tree, and this is like of a certain, heart disease, and you can see here things like heart rate, chest pain, cholesterol. We've got kind of age, things like that. We've got ECG, and all of these are used to build the tree. And as I said, the tree is actually, you build it on the training data set, then it's used to predict on the test data set. And we have to avoid overfitting. I've already explained kind of the training error. Now, the book, this is a little bit beyond what we're going to be doing, but the idea is across all the classes, we want our probabilities to be kind of close to 1 or close to 0. So if we have this equation here, if my probability, if my probabilities are either 0 or 1, say we have a 0 here and we have a 1 here, then this is going to be very low. If they're around 0.5, then this is going to be high. And kind of the same thing with cross entropy. Again, if we have class probabilities are nearly 0 or 1, then we actually have an entropy near 0, which is what we're looking for. But again, we can kind of get this, lower and lower and lower, and eventually we overfit. So a bit beyond what we're going to be discussing, but most of the algorithms for tree fitting will have its own built-in cross-validation. So it will kind of do its own cross-validation to make sure that the tree doesn't get too big before you can do your own cross-validation. So that's the tree methods. So it will actually, what it will do is it will look and it will like do a cross-validate, it'll do some cross-validation, and it will try and find the optimal size of the tree on the test data set. Okay, so what are some advantages and disadvantages of tree methods? Well, they're probably even a way even easier to interpret than regression, and certainly easier than discriminant analysis, because you're just looking, we classify based on variables of, values of your source independent variables. And it's quite often, similar, and this is a little bit into psychology. It's similar to how humans make product decisions. They will look at the different features of products, and eventually they will go through and then decide, I don't want this house, for example, because this house has like less than 2,000 square foot. I don't want this house because the lawn's not big enough. And eventually I would go through all my different features until I found my ideal house. So this decision tree is a little bit like human decision making. Another advantage is that we only use some of the most important features if we're not overfitting. So we can remove, it automatically performs some sort of feature selection. But the disadvantage is on pure classification performance, particularly in cases where the dependent variable will kind of depend on multiple independent variables kind of multiplied together, where there's some sort of interaction effect, then the performance is not very strong at all. So let's go and let's run some tree methods. So again, just make sure you're in the right directory and you have my helper function installed. And we're going to kind of use the rpart function today, but we're going to use for the trees, but we're going to use a few others. Okay, make sure we have the libraries installed. Okay, so let's go back to we've done each of our other methods on this auto data set, so let's do it again. So we've loaded in auto. And this is our auto data set from before. And this was part of the ISLR, so we didn't have to load it in from a CSV. And we have horsepower, weight, displacement, acceleration, and cylinders. And again, the idea is we have our dependent variable. We just basically make it into more fuel economy, cars with fuel economy greater than the median, and for cars with fuel economy less than the median. And we kind of have that as our dependent variable. So let's just have a look at this. And then we have this indicator which we're trying to prove is that do we have fuel economy greater or less than the average. So we can build our model using the rpart function. It looks a lot like regression. We got our dependent variable here, this fuel economy better or worse than the median. We're using all the independent variables. We've got our data set, and we're looking to get the class. Now this is because these trees can also be used for regression, standard regression. So here we're just specifying it's used for class prediction problem. Now, before we do any prediction, we can actually draw our tree using this function. This is why we had rpart.plot as one of our libraries. And we can actually draw a picture of the tree. You can actually look at the help file for this to get all the parameters, but it does have different modes. And first I'm going to show you the extra equals true mode, and then I'm going to show you the extra equals auto mode. So here's my tree. And this is very simple. It was a very simple problem. So we have, okay, is my car's displacement greater or equal to 191? If yes, then we predict that the car has worse fuel economy than average. And in fact, 164 out of 170 cars had fuel economy worse than average. So just the big cars had worse fuel economy. It's amazing, isn't it? And of the smaller cars, because you can have small sporty cars, if the horsepower is greater or equal to 97, which I guess is maybe a new car, then we have fuel economy greater than average. Now we have the actual weight of the car, and if the weight, so if you've actually maybe got a car with smaller displacement but with bigger weight, If it has high weight, then 13 out of 18 have lower than average fuel economy, so we classify it as lower, and the remainder are classified as higher. You see, at each of the nodes, this classifies as 0, lower than average fuel economy, is coloured green. Anything that any node that's classified as higher than better fuel economy is in blue. And you can see that these are like 90+%, these two nodes. These nodes are a little less strong, and they're actually in light green and light blue. Let's look at the other kind of interpretation of this. Okay, so this has got, actually says, this is a class, it's classified as 1. Now, it actually has the proportion of the class which is true. So this is 92% 1. This is 4% 1. Now, how do I know which way round it is? Well, you can work it out from this. If I'm classified as 0 and I'm 0.04, this means that obviously this 0.04 is not for class 1. So again, if I'm classified as 1 and my probability is 0.92, so a positive probability over 0.5 gives you class 1. This is going to be the class 1. This probability is the probability of class 1. And this number at the bottom, this is just the proportion of the training set at the node. So 47% of the training set is here, 43% of the training set is here, 5% is here, and 5% is here. So we can actually do the accuracy in a similar way as we did in previous weeks. So this is exactly the same code I ran as before. So we take the sample, and what we're gonna do is we're basically going to take a training set, as before, of 50% of the sample. So exactly the same code as previous weeks. We're going to run this on the training set, so just on auto 3 for the training set. Then we're going to predict on the test set, so rows that are minus train. And then we're going to run my little class evaluation function, and we're going to get the accuracy from that. And then we're running it 100 times, so we're going to estimate the accuracy over the number of runs. So the accuracy is 89%, so almost identical to the other methods we did before. Now let's go back to our friend, the consumer survey, which had like movie preferences and music preferences, a lot of those, and it also has gender, so we're actually trying to predict gender here from movie and kind of music preferences. So let's load in the data set. So here, and let's just, if you can't remember what's in it, let's just have a look at basically a load of just different preferences for different types of movies and music. Okay, so what we're going to do now is we're going to have gender. We're going to predict gender, again, using our part and the computer survey. So here we're just taking the whole data set as the training data set. And we're going to have our first interpretation. Okay, so this is actually a bit more complicated classification. So let's just go for one of these nodes. Let's just do one of each. So this is a no, so I'm less than 3.5 on liking romance. So it's always yes to the left and no to the right here. I'm greater or equal to 3.5 for war. So it's a no to war is less than 3.5. And I'm a no to action equals less than 3.5. So if I don't like romance movies, I like war movies, and I like action movies, then 138 out of 156 is male, so we classify as male. Conversely, if I'm greater or equal to 3.5 on romance, and yes, I am less than 3.5 on action, then I'm classified as female. And 236 people out of 254 people in that bin are females. So again, remember, important things to remember. Yes is to the left here, and no is to the right. You go to a node, you will look at the kind of the inequality, And if it's kind of no, then you flip it. So here it's romance is greater or equal to 3.5. So this branch is romance is less than 3.5. And the yes branch is romance is greater or equal to 3.5. Now let's just look at the proportions. Okay, again, just to make sure you're 100% sure, this probability is obviously the probability of being male, because when it's greater than 0.5, we classify as males, and it's less than 0.5, we classify as females. So here, this kind of node has males. 88% of the people at this node are males, and this contains 17% of the data set. And again, this one we did before. Here, at this node, we classified as females, and 7% are males, and this contains 28% of the data. So now let's go and let's just do exactly the same as before. But this time we're also kind of basically getting the classification table. So we use the table command based on our prediction and the actual values to get the table. And what we're going to do is we're basically going to add the tables together and divide by the number of tables. So here we're just getting a bit more complicated. We get the accuracy using my class eval. We get the table using the table function. We kind of add them all together and we divide by the number of runs. Okay, so you can see we on average we get a prediction of 75%. So okay, not amazing. And you can see here, for example, we've got the females. This is the females we've classified as males, and the males we've classified as females. So again, you can build a reasonably, if we did this randomly, we'd get around 50%. So our model has some usefulness. But it's quite hard to predict. You have some males who like, romantic romance and kind of Latin and pop music, and you have some females who like sci-fi, war and action movies. So it's not a perfect classification. Okay, so let's just finish here, and then we're going to talk a little bit about unbalanced problems in the next